did not get posted the audio version until just recently. However, I will tell you that the slides really didn't have much change in them. I did find one error in the slides that I had to resolve, and we're going to talk about that as we get in. So with that, were there any questions from the slides from practice number 6? Keep in mind, this was the one that was on electrical fields, electrical charges, etc. Now I'm going to type it into the thing. Any questions from the slides on practice 6? And while we're waiting for everybody to join us, I'd like to wish everybody a very happy Veterans Day, and thank you to any veteran coaches we happen to have out there. It's a very special day. I'm very proud of my service that I was able to do. And it's just an important day to think about all those that sacrificed for us. That's okay, Chance. Don't worry about being able to do them. Would you like for me to go through them quickly? Would that be preferred? Okay, Mr. Balanis. It took me last time for the formula on the last homework question. Okay, well, then I tell you what, we're going to do that. We're going to go over the slides. Please put any questions you have as we go through them, okay? Okay, so as you see, we've got Circuit Lab. And here I'm going to. Okay, so let's talk about very quickly, what is an electrical charge? An electrical charge is got the physical property of that it will be attracted or repulsed by an electric field. And you'll notice we put a positive charge, it's a circle of a positive, and a negative charge is a circle of a negative. Okay, so here's a positive and here's a negative. You'll notice that the way we draw field lines is that the field lines from an electric charge radiate out like a sun, direct, and they actually go on for forever, okay? But just like the radial lines, as they separate, the electric field actually diminishes as we get further away. Now, negative charge, the lines come into it. Sometimes some people have said exactly like a black hole. And when you draw them nearby each other, you'll notice that they go from the positive over here to the negative, much like you would expect a north and south pole to work. Okay? And you'll notice that on the other side, you do have some lines that go out, and you have some lines that come in, but the majority of them loop back to each other. The unit of charge is coulombs, okay? And you'll notice that an electron has a charge of 1.602 times 10 to the 19 coulombs. That's actually one of those things I'm going to expect you to have in your binder, and that's the type of thing I would expect you to be able to tell me in your binder check. Okay? It's very important to be able to draw electric fields just like we drew magnetic fields. Coulomb's law is basically the force is equal to Coulomb's constant times charge 1 times charge 2 divided by r squared. And r being the distance between the two charges. Keep in mind that it's not always a single element. It could be like an ion, or it could be an object that has lots of charges together. Okay, so it's it's sort of the central point of the ion. Another thing I would write down is that Coulomb's constant is 8.99 times 10 to the 9th Newton meter squared divided by Coulomb squared. Okay, it's very important that you also have this formula written down. And the other thing I'd like you to notice is that if you think it looks a lot like a gravitational formula, that's very good. It does go down as r squared. So one of the questions I'll ask is that if I move it from X meters and to 2X apart, how does that impact the force? And you'll notice that the change in the force when I move out twice as far would be 1/4. Okay. And here's how you can note that the forces, they push apart when they're the same charge. So if they're both positive, in this case, they push apart, and so they're repulsed, and then they're attracted if they're positive and negative. And if they were two negatives, they would also be repulsed. So, but let's talk about what is a capacitor. A capacitor, and this may only be in Division C, but when we talk about capacitors, capacitors are usually indicated by these icons here, which generally show parallel plates with a material in between them, okay? And what it does is that it keeps electric energy stored in charge, okay? The units of capacitance are Faradays. In most capacitances, the capacitors are really, really small items like this right here. You'll notice that this is 4,700 microfarads, okay? And you'll notice most of these other ones are really, really small amounts of capacitance. So you see microfarads, you'll see picofarads. And the one thing I want you to remember is that, and this is another one to write down, that the charge is equal to the capacitance times the voltage. Sometimes you'll get the charge and you'll be asked to solve, and you'll be asked to solve for the capacitance. And if I have the charge and the voltage, I can do that. Sometimes you'll be asked to solve for the voltage. Sometimes you'll be asked to solve for the charge itself. The other thing to keep in mind is that this is a normal fixed capacitor. This is what's called a polarized capacitor, which this is where the positive charges would be located, and this is the negative side. And then this right here is a variable capacitor that looks something like this, quite often used to tune radios. Okay. Mr. Cantos, please don't talk about movie items here because we're trying to cover this as quick as we can. So another thing that you can look at with a capacitor, okay, is that it's usually two different plates separated by a small distance d. D is always a lot smaller than the surface area of the two plates. So the thing I want you to keep in mind is that there's these two plates with some sort of dielectric in between. And dielectric is a non-conducting material, but that's where we're going to put all of our electric field at. So all the charges get on one side of the plate and the opposite charges get on the other side of the plate, and then they create an electric field through that dielectric material. Remember, Q is equal to CV, okay? And then whenever I talk about D, I'm talking about the distance between the two plates, and then A, I'm talking about the surface area of the plates. So one thing to keep in mind is that I may ask you to, given the dimensions and the materials, tell me what is the capacitance. And that is equal to C. The capacitance is equal to epsilon times A divided by D. And epsilon is the dielectric permittivity of the material. So that determines how much capacitance or how much electric field can be held. Keep in mind, you do not want a conductive material because then all the charges will just go from one side to the other and you won't have any capacitance at all. The energy stored in the capacitor is E is equal to 1/2 CV squared. Okay, that looks like the old formula for if that looks like the old formula for kinetic energy, you're not alone in noticing that. And so I would say that these are also important things to put in your binder, as well as the permittivity of air or free space or vacuum is 8.854 times 10 to the minus 12 farads per meter. Okay. All other materials are going to have a slightly higher, or sometimes in some cases, much higher permittivities. Okay. And so if we had a glass capacitor or we had like a plastic capacitor, all of those. So one of the things I'd like you to do is to draw the field lines for these ones right here. And so what if you'll notice here is that in this one, they would all come out rays outward like the sun. Here, it'd be all rays coming in, straight in, like a black hole. In this case, you would have lines that would go from the positive to the negative. So from the sun to the black hole, if you will. And these two would be attracted to each other because they're opposite. In this case, I would have all the lines, if you will, all the lines would end up going from one to the other. Okay? And so they'd all be pretty straight. So therefore, what would end up happening here is that you'd have solid attraction between these two and all the electric field lines in between. Here, the field lines, you'd have it all coming in from the outside, but there would be nothing in between here. And so these would actually be repulsed from each other. Now, do you remember whether this was a voltage or a current splitter? Okay, if there's a question about the energy required to remove a dielectric medium from capacitor, how would that be calculated? Okay, so if there's a question about the energy required to remove a dielectric medium, are you talking about if we change the dielectric medium? You might want to calculate the energy with one dielectric medium and compare it to the energy with another dielectric medium. Very good question. That's right. What we were looking at was a voltage splitter. Okay, had the same current throughout. Now, let's look at this question here, another in-practice quiz. You've got two electrons, they're 1 millimeter apart, so they're actually quite close. Now, not by electron terms, but by normal terms they are. And what you'll notice is that if I have two electrons, are they attracted or repulsed? Let's see who can answer that. Are the electrons attracted or repulsed to each other? Anyone? One answer, repulsed, repulsed. That's right. They're all going to be repulsed because they're the same. Now, the force between them, let's see if anyone can calculate that. Assume that they're in air. And I'm going to get my calculator. It's actually going to be a very small amount of repulsion. Oops, sorry. So it's going to be a very small amount of repulsion. And let's go back to our formula that we want to use. It's going to be Coulomb's law. Okay. And it's this. So it's 8.899 times 10 to the 9th here times, and you remember what the charge was? 1.602 times 10 to the 19th, and there's going to be two of those. So if I take 1.602 E19 squared times 8.99 E to the 9th, and then I get divided by R squared, which is divided by 1. So I get the number 2.3 times 10 to the minus 22nd newtons. Does that sound about right to everybody? 2.3 times 10 to the minus 22 newtons. So a very, very small amount of repulsion. Okay? Okay? And if we were to draw the electric field lines, since they're both negative, all the lines would be coming into both of them, okay? And there would be no lines in between them. The two protons, it's the same thing. They're now repulsed because there are two positives, except now they're two suns that are both putting out rays. The force is exactly the same, which is very small. And then we could draw the electric diagram. If it's electron and a proton are 1 millimeter apart, are they attracted or repulsed? They're going to be attracted. The force is the same, except now the force is pulling them together. And the electric field line now actually has lines going from one to the other. So, a couple of the homework questions are used to know what the common materials are used to charge materials: silk, cloth, glass, etc. Keep in mind, Benjamin Franklin was famous for his experiments involving taking a glass rod and a silk cloth and transferring the electrons from one way to the other. Okay. Talk about how you can do positive and negative and which one provide negative charges. Explain how a balloon that is rubbed on someone's head sticks to the ceiling. And what it does is that you're charging it with charged particles, and then it's inducing an electric field on the other side and on the ceiling, much like how our magnet induces magnetism on iron. And so what that ends up causing is that it causes a sort of like a capacitance, if you will, that holds them together. Okay. Talk about common ways to prevent static charge or discharge. Draw the electric field lines for positive, negative, and mixed charges, and determine the force between 10 Coulomb and minus 100 Coulomb set of charges that are 1 meter apart. Now, them being 1 meter apart, that's going to mean that they're going to have very, very little attraction. Now, since one's positive, one's negative, they're obviously going to be attracted to each other. But the thing to keep in mind is that I want you to get used to the concept of the further apart we take two charges, it drops off as 1 over r squared. Mr. Dazzy, I'm gonna have to take your word for it because I didn't do the calculations myself. But the key thing that I'd like you to remember is that when you're looking at these charged particles, okay, be able to draw the field, be able to figure out the energy in the field, be able to figure out the force of attraction, and be able to figure out the capacitance. If you can do all of those things, you'll be able to do everything we need to do for Division B. Now, when we get to Division C, we're actually going to be talking about the RC time constants. All right. Well, it looks like we're going to have to actually do some calculations now. Okay. So this was for the last thing, which was the force between 10 coulombs and 100 coulombs. Okay. So if I take 10 coulombs times 100 times, I got to get Coulomb saying 8.99 to the 9th. I am afraid I agree with Mr. Ballas. I get 8.99 times 10 to the 12th. Okay. So the other thing is that what you usually do, okay, well, think about it. Let's look at Mr. Dazzy. You made the calculations. I'm never going to get upset for making your calculations. Always make sure you show your work. You never know when it will help out. But if you look, I take 8.99 times 10 to the 9th times 10 times 100. Okay. Well, that ends up being 10 to the 3. And so that's 10 to the 12 divided by r squared. And this is where I made the math a little easier. R squared, 1 squared is 1. So you divide any number by 1, it's the same. So that's how it comes out to 8.99 times 10 to the 12th. And then you either think about whether they're attracted or repulsed. Okay. Is it negative 8.999? No, it is 8.999 towards each other. Okay. So they're being attracted 8.99. So it's not really a positive or negative thing. And you'll notice that quite often what they'll end up doing is that they'll end up putting the absolute value signs over them. Nine. Okay, so you rounded 8.99 to 10, so that's how you got that. Yeah, Mr. Dazzy, where you made your mistake is that 10 to the 9th times 10 to the 1 times 10 to the 2 is 10 to the 12th. Okay, so that was where you made your mistake. Don't feel bad. That's really close, okay? You got really close. And trust me, it's always, this is why we always double check our numbers. You were really close. And if you think about it, the difference between 9 and 8.99, you're within, less than a percent. So you're actually quite close, okay? And depending on your event supervisor, like you have me, I would have definitely have taken that. Okay. However, let's say I double the distance, okay, to 2 meters now. Okay. So if I double it to 2 meters, what is the force? Okay, I got it. So the correct answer is 8.99 times 10 to the 12th for 1 meter. If I double it to 2 meters, what did I have to do? That's okay. What I ended up doing was I divided it by 4. Okay, because I divided it by 2, and then I divided it by 2 again. That's the same as dividing it by 2 squared. And I come out with 2.457 times 10 to the 12th. That's right. Okay. The types of questions that they'll quite often ask are like where they'll double or half the distance between the charges. Okay. Now, were there any questions about drawing field lines? Good. I'm glad everybody got that one easily. Okay. Now, you will probably notice that drawing magnetic field lines and drawing electric field lines, once you get used to it, you're like, okay, this looks very simple. But it's very important because when you are in a competition, the easy questions quite often count as much as the hard questions. So the difference between the teams that win all the time and the teams that sometimes win but lose a lot more is usually in the easy questions. The teams that win all the time, they never miss an easy question. They double check their answers. They work well in a team. Okay. So they're able to answer all the easy questions without fail. Okay. The teams that get themselves into trouble are the ones that are sort of up and down when it comes to easy and difficult questions. Okay. So, let's see. With the next question I have is that we're going to do a binder check. It looks like this was the one practice that I sort of shoved in. It was a little extra practice because I really didn't talk enough about Lorentz force law or Coulomb's law, and we'll talk about how to use Coulomb's law in conjunction with magnetic force later. But that'll be in the next practice. But let's do our binder check. So everybody get ready with their binders. And the way we do it, for those of you who have not done a binder check, is I will call out something and you will have 10 seconds to find it in your binder. And as soon as you find it in your binder, you write in either the answer or say, I found it in my binder. And this is a way so you can get used to finding stuff quickly in your binder. Okay? So the first thing I'd like you to find in your binder, everybody should find in their binder, the rules. Go. Okay. Found it. Very good. Very good. It's very important that you can find it in your binder. Okay. The next thing I want you to find in your binder is Ohm's law. Go. Very good. All right. Now, I want you to find in your binder the formula for power if you know voltage and resistance. Go. The formula for power and resistance, or the formula for power if you know voltage and resistance. Write it down. Sir Flim Flam. Oh, Mr. Dazzy, very close. V times I is power, and but Mr. Katz got it right. V squared divided by R is when you know voltage and resistance. Okay, VI is when you know voltage and current. Okay. What is Coulomb's constant? Go. Or write it down, Mr. Dazzy. And if you don't have it, that's okay. But that'll just be an important one to have. Okay. So you should have been able to find Coulomb's constant. And if I look at it, it is 8.99 times 10 to the 9th Newton meter squared divided by Coulomb squared. Okay. That is Coulomb's constant. Okay. What is the energy stored in a capacitor? Go. That's okay. That's okay. You're doing just fine. Find the energy stored in a capacitor. It reminds me very much of the kinetic energy in mechanical motion. Anyone? That's correct. 1/2 CV squared. That is correct. Okay. What is the formula for capacitance if of an air semiconductor, or excuse me, an air capacitor? What is the formula for the conductance if I know the area and the distance between the plates for an air semiconductor or an air capacitor? So sorry. Oh, Mr. Ballas got it. Okay, so that one there is C is equal to epsilon A divided by D. It's very important that you make those epsilons correctly because they can sometimes look like an E. Okay, and keep in mind that since it's in the air, the epsilon is equal to 8.854 times 10 to the minus 12 farads per meter. This is again something that you're going to want to have written in your binder. And now for our history check, I'm going to let, since Mr. Ballas and Mr. Katz and Mr. Dazzy have been answering all sorts of good questions, I'm going to let you guys ask one history question from your binder and see if the other people can find it. So let's start with Mr. Ballas. Write down any history question you have. Write down any history question you have, Mr. Ballas, and let's see how fast the other folks can find it. And while we're waiting, Mr. Patel asked me a question about if I have to know about Thevenin stuff. Okay, here's the deal about Norton and Thevenin equivalent circuits. We are going to cover them. They're actually not that far away. We've just about covered everything that you actually have to have in Division B, okay? Norton and Thevenin are not required in Division B. However, knowing how to do a Norton and Thevenin equivalent circuit can help with circuit analysis. I'm going to go over it. I recommend that the Division B people listen to that. I recommend that they listen when we start getting into superposition and some of the other topics that are usually not considered Division B topics, because they help with circuit analysis. Who developed the AC motor? And the answer is Tesla. You know, I'm not positive. I don't have a binder. That sounds about right. Because wasn't that the thing that Edison promised him $50,000 for doing, and then Edison wouldn't pay him? Yeah. Edison, great inventor, great scientist, great businessman, not always the nicest person. So Tesla is our answer. Sounds very good. Very good. Okay. Mr. Dazzy, do you got a good history question for everybody? What was one thing that Faraday invented? Now, that's a dangerous question because Michael Faraday invented like a lot. So if everybody can just answer one thing that Faraday invented, it can be any of the things. The Faraday cage, yes, okay. The motor. I'd probably stick with the motor. One of the things really interesting about Michael Faraday, he was not classically trained. He was self-taught. He went to go work at a bookbinding company, and so he could read all the books, and he taught himself chemistry and physics. And he kept writing to the top scientists of the day, and nobody wanted to really listen to him because, well, he'd not gone to college or even high school. And yet when they started to look at his stuff, they realized he was really quite brilliant. And he was one of the top minds of the day, even though he'd never gone. Electromagnetic stuff was the answer. Okay, probably they're going to ask something a little bit more specific than that. But again, keep working on your binders. Also, as we are now getting really close to when you're going to be in competition, we're going to be starting to go a little bit quicker on some of the items. And like I said, when we get to Division C topics, there are going to be times where we'll be covering stuff that is not Division B. And so the only thing I'll ask is that if you're a Division B person listening in, none of it is bad stuff to know. But if it's not part of what's required for you in a test, I would not spend a lot of effort and energy. I'd focus on the things that really apply to you. Are there any other questions about anything involving Circuit Lab? Since we're going a little bit ahead of time today. What if you're taking the test by yourself? Good question. I have seen people do very well taking the test by themselves. It's always good to have a buddy, you know, that the lady or gentleman sitting next to you can check your work. Even if they don't know very much about the subject, they can help you look stuff up in your binder. Who helped establish the photoelectric effect? Well, that one's pretty easy, and I happen to know that one. That one happens to be Einstein. I forget who he did it in conjunction with, but that's actually what he won his Nobel Prize for. So the thing I would say is that if you're taking the test by yourself, okay, you're really going to have to, that binder becomes your partner. So make sure that binder's got all the information that you'll ever need to look up. And if you write it in your binder and you have it properly highlighted and properly tabbed where you can find it quickly, don't feel like you got to memorize it. Okay. How much should you know? You should know as much as you can. And don't just talk to me, talk to other coaches, talk to your own science teachers, talk to parents who might know some of this information, because you don't know who's going to write the test. If I'm going to write the test, I'm going to write it one way. The way I would recommend to check yourself is to go to sciali.org, download some of the old tests, take those. If you're making 100 on all the old tests, you're probably in good shape. If you're missing a few, it tells you what you need to study. Hertz was the scientist on our list. Okay. Would you recommend to print the PowerPoints or take notes on them? I've been taking notes and I don't think I have everything I should. All right. Whatever works best for you. I know that some of my students would actually print out my notes, but here's one of the things they would do is that when they printed out the notes, okay, they would come over here and they would, when they went to print, okay, they didn't just print them whole page to save paper. Da, da, da. And of course, it's giving me issues. But basically, they would print two at a time, and they'd print them double-sided. And then they would write notes on there. Okay? You have a tourney in December 7th by yourself. Should I master a few things or cover everything? All right. Here's my recommendation. Master the basics. Know Ohm's law. Know your power equations. Know how to do basic circuit analysis. Okay, know how to do all the things that we've done. Go through the homework generator up through level 5, at least. Have that stuff cold. As you find more history stuff, slap it in there. Okay, the history stuff is one of the few things that you can probably catch up on with faster. Okay, and best of luck on that one on December 7th. I know you'll do great. It's an invitational. Those are the best ways. You'll find out where you're at. And I would do a lot of practice tests. And when you do a practice test, time yourself. When I would give my kids a practice test, I'd always give them 30 minutes to do it because I knew that they'd always have more than 30 minutes. But then that way they got used to working at speed and working faster and working faster. And then we could figure out the areas where they were weaker. Can you put the powers in the grinding point and bring them to test? Absolutely. Just make sure they're in the 3-hole punch or put them in a protector. So like if I'm going to print these out here, what I'll normally do is that instead of trying to do them in color, I'll do it pure black and white. Okay. Instead of full page slides, if I want to write my own notes, I can say slides with notes. And then what it will allow me to do is that it's thinking about it, but it's going to actually allow me to do the printout with that. But you notice when I say print out in pure black and white, that's much easier and it prints out better. Okay. Okay. I can also tell it to print 2 at a time. The Chattahoochee Invitational, is that in Georgia or is that in Florida? Should we include a table of dielectric constants in the binders or would that be given on the test? Yes. Both answers are correct. I would have that table of dielectric materials available. Okay. And if they give it to you on the test, that's the number you use. Never use the number in your binder if they give you a different number. So if I tell you that the dielectric constant is 3, okay, on the test, and your note says it's 2.996, forget the 2.996 business. Go with whatever's on the test because that's what they use to make their key with, okay? It's in Georgia. Well, best of luck to you. I know they got some great teams in Georgia. They got a lot of great teams in northern Florida. They've also got some really good teams in the Carolinas and Alabama. I imagine you're going to have some really good teams. And given that you've already been putting time into this, I know you're going to do fine. So if you look here, if you print out with notes pages, you'll notice that it prints it out and you got plenty of room to write your notes down here. But my personal favorite is to do 2 slides at a time. And then when I print on the front and back, I can get 4 slides per page. And then I just drop it in a sheet detector. And then if I want to draw over here, I can do that. And so for these in-practice quizzes, I would draw like the lines, from the positives to the negatives, or the positives out or the negatives in. And I would go over it with your coach so that you've got this stuff in there. Okay. But again, find other materials, whatever helps you. Okay. All right. Any other questions? You can email me with any questions you may have. You can also ask here. The best thing I can recommend, study. Go over what your coach has provided you. Go over what we've gone over here. Okay. The other thing I would recommend is do a lot of practice tests and never give yourself the full 50 minutes. Cut it back to like 30, 40 minutes so that you can get used to working tests quicker. And if you're always getting at least 90% on each test, you're probably okay. If you're getting 100% on all those sample tests you find on Ciali, you're golden. You're ready to go. Number one thing, when we get down to actually doing the test, the most important thing I can tell you is practice such that you're calm. You want to be nice and calm. You want to have your calculator ready. You want to have your pencils ready. You want to have your binder ready. Get there early so you're nice and calm. And when you take the test, listen to what the event supervisor is going to provide you. Because a lot of times they'll throw out a whole bunch of other stuff. And just, if they tell you, hey, make this change, you make that change to that question right then and there. And then you go through the test in a very methodical way. Make sure you answer all the easy questions. No problems. The harder questions you come back to. But make sure you answer all the easy questions, because you don't want to accidentally not answer an easy question on the last page. Okay? That you could have gotten easy points. All right. And so my email, and let me send this to you, is go15@hotmail.com. Do I know the Piedmont team? Yes, I do. Very good team. Really nice kids, really well-coached kids. And, honestly, I'll have to say I've done this at nationals, and I've done it in multiple states. And I have always been impressed by the professionalism of all the coaches and just the sportsmanship that you see amongst all the teams. They're your rivals. Well, if you study harder and you answer all the easy questions and you're ready for the medium and the hard questions, you'll give them a run for their money. Okay? We came in third. That's pretty good, but I know what it means to go for first. And so the best recommendation I can have is try to get a partner. Even if that partner is just holding your pencils at first, it always helps to have a good study partner. It always helps to have somebody looking over your shoulder in case you make a mistake. Somebody who's if you're like me, like I make mathematical or arithmetic mistakes quite often. So that's why I write and show all my work. But if I get somebody looking over my shoulder, sometimes they say, hey, Rush, you made a mistake. All right. Any other questions? Do I know Boca Raton? No, I do not. But I'm guessing they're good if you're asking me about them. I actually grew up in the state of Louisiana, and Baton Rouge Magnet was our main rival. When we did good, we came in second to them. When we did poorly, we came in like fifth or whatever in the state. I went to a small school called Leesville High. I'm in the state of Texas right now. When I started in Science Olympiad, I was in Ohio. For the last 3 years, I was in Maryland, and then I just moved down to Texas. As an engineer, sometimes you have to move with work. Well, I wish you nothing but the best of luck, and I'm sure you're going to do great. Just remember, keep studying, and also study all your events, okay? You never know where your team's going to need your help, okay? Remember, in Science Olympiad, it's better to come in third place across the board than win first and then occasionally come in last. A last place will kill you. Okay, so always remember, whenever you're studying in an event, a lot of times you're studying in that event to help out your team, not because it's your favorite event. Any other questions? All right, everyone. I'll be posting. The plan is to have, we'll go over number 7, which we will go back to magnetism, and we're going to talk about induced magnetism with current. Okay. So that will cover all of the electrical and magnetic forces and how to create and generate electric and magnetic force. Well, there's many power formulas. Okay. The power is equal to V times I. Power is equal to V squared divided by R. It's equal to I squared times R. Okay. And, that's the key thing and remember, sometimes it's real easy to know the voltage and real easy to know the resistance. So you use those two. You use whichever two are the easiest to know. Okay. Any other questions? Well, with that, good luck to everybody. And I want to thank all the coaches who've been reaching out to me and all the event supervisors who've been reaching out to me. I'm here for you. Oh, thank you so much. I will check that document later today. Take care, everyone.